Hey everyone, in this video we're going to be talking about rolling contact bearings and specifically looking at combined thrust and axial loading. And this video is part of a lecture series on mechanical design 2. So we're going to get started with looking at a cylinder and adding a bearing around the cylinder. So let's say we added a bearing around the cylinder in the middle. Doesn't really matter where we add it, but let's say it goes all the way around. And we're going to shade the area to show that it has some depth, and it would go all the way around. Now, typically, when we talk about loading on a bearing, we talk about an F that is going, or a force desired, that would be the force acting on the bearing itself. And typically, this is called FR or F radial. So the radial component of that force is called FR. And we can then find this axial load, and we can find the optimal axial load based on our bearing, or vice versa. We can have a force desired and then choose a bearing that will withstand that force desired. Now, what we haven't taken into account yet is, so far we've seen that forces on bearings are essentially happening at a radial component, so it goes towards the middle of the circle of the bearing. However, there's a second force that can happen on bearings, which comes from the axis of the cylinder. So there is a second component of that force that is called the axial component. What the axial component of the force is sometimes a bearing is going to move, or is going to have to resist the movement back and forth, or it could be one force, or it could be a cyclic force that's axial. Typically, the axial force is constant, so it could come from gravity, for example. So if you have a bearing holding something together, there could be some sort of force due to the weight of the cylinder that it's bearing. So what we need to come up with is, so far we've been able to solve for problems where we have a force radial. Now we're going to start looking at problems where we have a force radial and axial associated with our problem. So it's not always going to be the case that we have axial force, but sometimes we could have axial force. We're always going to have a radial force, however. So if I draw a cross section of our bearing from the side, so let's say we have a cross section with the ball bearing or the roller bearing here. Okay, we would have both sides with, so I'm just cutting a cross section of the system where we have the bearing. And essentially, if I simplify my drawing, I have a force radial that's occurring at the top, and then I have a force axial that would be occurring here and affecting essentially our bearing in this way. So we would have our force axial affecting the bearing. And the resultant force ends up being, so we'll call this F resultant. Okay, this resultant force ends up being a force at a certain angle. Okay, so whenever we have combinations of loading, so I'll keep in color here, so combinations of loadings, we actually come up with a new term called F sub E, which is representative of the equivalent radial load. So F sub E that we're going to be using is going to be a equivalent radial load. So that means that it's going to be whatever radial load we would put through the bearing if we had a axial load together. So it's usually going to be higher than our original radial load, but it's not going to be in the direction of the resultant load. Okay, so we're not actually going to be solving for the resultant load and then using the resultant load, because that would require us to redefine all of our mathematics and all of our theory based on bearings. So what we do instead is we say, if the axial load is big enough, what we're going to do is we're going to add, and I'll put it in blue, we're essentially going to be making an FE that's going to be greater than FR, and is going to affect the bearing in the same way as FR, and it's going to be an equivalent. So it's actually a shortcut way of saying FE is essentially equivalent to, it's the equivalent of the radial load that does the same damage as the combined loads. So let's look at an example of this, or a quick definition of how we're going to write this. And I'm going to write it down just so that we have it for our notes as well. So we can say that FE is equivalent, and this is how they calculate this and how they come up with the theory for this, but it's equivalent to the radial load that does the same damage as the combined loads. So what experimentalists did for the ABMA method and in general in the ABMA association is they said, well, we're going to essentially test a bearing with a radial load of, let's say, 1 kilonewton, and then an axial load of also 1 kilonewton, and then we're going to say that we're going to test that, figure out the damage that happens, and then we're going to do another experiment where we just have a radial load. And we're going to make this one, the one on the left, we're going to make it equal to whatever damage is equal in terms of the radial load only. So for example, in this case, the radial load could be, so let me just redraw this arrow. So the radial load could be essentially the equivalent load of 1.5 kilonewtons. So essentially what we're saying is we're saying that and this is just an example, it's not true, it's just an illustration of what's happening, okay? We can say that, for example, if a bearing has a load of 1 kilonewton in axial and 1 kilonewton in radial, it would be equivalent in terms of damage to a radial load alone of 1.5 kilonewtons. Okay, so hopefully that makes sense. And it'll make sense when we start doing examples, but it's just a mapping of the axial load back into a radial load so that we can use the same theory, essentially. Okay, and they did a bunch of experiments at different loads, and they found a correlation between how much axial load there is and what equivalent load would be equal to. So it's not exactly 100% accurate in terms of theory, but it works in practice thanks to our correction factors and thanks to the following table that we're going to show. So a couple of different notes about this new equivalent force that we're talking about. So if we have inner or outer rotation, so depending if the inside is fixed or the outside is fixed of our bearing, we will have different results. So we're going to have different load effects, which we'll explain through an example problem later on in the session. And these load effects are going to be determined by a term called V. So V is going to be equal to 1, and I'll put 1.0 just so that we don't get confused as V is equal to something else. But V is 1.0 for if you have an inner ring rotation. V is going to be equal to 1.2 for outer ring rotation. And V is going to be equal to 1.0 if you have a self-aligning bearing. And self-aligning bearing is a different type of bearing, but you could have that in a question, but I'll invite you to look up what a self-aligning bearing is. There's also that information in your book if you want to. And what we can come up with is a graph showing the correlation between your F equivalent and your F radial, essentially. And what we're going to find is we're going to draw a graph that follows. So we're going to draw, based on experiments, we're going to draw a graph of FE over VFR. Okay, so it's FE over F radial, and then we're going to map it against an FA over FR. Okay, so we're looking at the difference between F equivalent over FR with the V accounting for if we need it, and then FA over VFR, which is the axial load over the radial load. So we would expect as the axial load increases in comparison to the radial load, so as the percentage of axial load increases over radial load, which is this term right here, we would probably have a higher equivalent load, okay, which would mean that essentially this term would go up, okay? This would be our expectation. Now, in real life, we actually see the following. So we see that the line actually looks something like this, and we'll analyze what this line means, okay? So it looks like this, and then at some point, there is a cutoff point where we start having a straight line going up, okay? And so what we can do is, if you look at the actual data points of our testing, the data points usually look something like this, and we have some data points going up, and it's basically a curve fit through the data that we see, okay? So if there is no axial load, the first thing we can write is that if there's no axial load and FA over VFR is equal to 0, then we would have that FE over VFR is equal to 1, okay? And obviously there is no F equivalent if that's the case, okay? So FE over VFR would be equal to 1, and we can just write that FE would actually be equal to FR. So we're not even going to take into account the V. So the V kind of cancels. We don't even take into account, okay? So that would be all the problems that we've done up to so far would be defined by this term. If there is no axial load, we have FE over VFR would be equal to 1, or FE is equal to FR because we don't even have an axial load. Now, as we start introducing an axial load as a percentage of the radial load, so initially the axial load is very, very low, we have this straight line that goes along a constant value of 1, okay? So that means that as we start going along and start moving along this line right here, we can see that the line is a constant. So we can say that FE over VFR is equal to 1 for FA over VFR is up until this point, okay? And we're going to call this point E, okay? So if for FA over VFR is less than E, we have that FE over VFR is equal to 1. So essentially what that means is if you have a inner ring rotating, let's keep it simple, and we have an inner ring rotating system. If we have an inner ring rotating system, what that means is that FE is basically equal to FR up until a value of E. Okay, and we'll talk about what that value of E is. It depends on what bearing you have. Okay, so we have that essentially there are no effects from FA if FA over VFR. So if the percentage of FA is very low compared to the percentage of FR, then we know that there's no effects from FA. So let's think about it. For example, if we had a load of 100 newtons in radial and 1 newton in axial, the equivalent is probably just going to be equal to 100 newtons. There's going to be no extra effect from the fact that there's 1 newton of force going sideways or going in the axial direction. Okay, now once we get to point E, we start getting a correlation that starts increasing our value of FE over VFR. So then we start seeing the effect of the axial load after point E. And this point E depends on a few different things. Okay, and we'll look at what that depends on. So what we can do is we can obviously curve fit the first part. The first part, curve fitting, is very easy. It's just equal to 1. And then what we can do is we can curve fit the second straight line. So we can curve fit this line if we want to, with a curve based on two different terms. So we have one term would be the y-intercept, and then this would be, which we're going to call x, and this would be the slope y. So they use y and x. I don't know why, but that's what they use. For the intercept, they use x, and for the slope, they use y. So that would give us a value of for if FA over VFR is greater than E. So once we get to any region from here, we would use an equation that solves for the straight line equation up here. So let's write some equations down, and let's write some thoughts down, okay? So first, let's write in black what we have. We'll summarize again what we have if FA over VFR is less than E. We then have the fact that FE over VFR is going to be equal to 1, which means that FE is going to be equal to VFR. Okay, very simple. Now, and I'll draw this in blue since we wrote it in blue on the graph. If FA over VFR is greater than E, then we have that FE over VFR is going to be equal to it's going to be equal to mx plus c, essentially, okay, or the straight line equation. So we have that the y term, which is FE over VFR, is going to be equal to mx, in this case m, which is your slope, is going to be capital Y, okay? So we have capital Y times FA over VFR plus our x, which is going to be our intersect of our y line, plus x. Okay, so we have these two terms. And then for different experiments, we can find the different slopes of the lines and the different intersects for the lines, and we can plug those in and find FE in terms of FA over VFR. Okay, it'll all make sense once we start doing an example, but it'll help us out once we start doing that. Now, another term that we need to know, and we'll do this while we solve the problem as well, is that C0 is going to be equal to the basic static load rating. Okay, and this C0 is going to be used as essentially a load that would start the failure of our system. Okay, so now going into this, we can now try solving problems, and we can try understanding what's happening in terms of solving problems and trying to solve for different cases. So what we're going to do is we're going to solve problem 1123, which is here in our notes. And based on our notes, we're going to solve this example problem in this video. So we're told that a 0-2 series single row deep groove ball bearing, so it's a deep groove ball bearing, not an angular contact, so it's a little bit different, with a 30 millimeter bore. See tables 11.2, so 11.1 and 11.2 for specifications, is loaded with a 2 kilonewton axial load and a 5 kilonewton radial load. So the axial load is actually 2 and the radial load is 5, so we do have some effect from an axial load. The inner ring rotates at 400 revolutions per minute. It tells us determine the equivalent radial load that will be experienced by this particular bearing. So let's start with determining the equivalent load. We're also given table 11.1. Table 11.1 says this is the equivalent radial load factors for ball bearings. And we have these different terms in this this chart. So we have FA over C0. Okay, C0 we'll talk about in a second, but it's a value that can be found for a bearing. We have the value of E, which is our threshold from switching to if FA over VFR is less than E or more than E. And then we have some values for less than E, and greater than E. And we can see that for less than E, just x1 is equal to 1, which is your intercept, and there is no slope to the line. The line is flat, okay, for every single term. And then FA over VFR greater than E, we now have an intersect, and then we have some different slopes associated with that. And we're also told at the bottom here that could be used sometimes, use 0.014 if FA over C0 is less than 0.14. So we have this table here, table 11.1. We also have this table available in our formula sheet. So if you want to use the table in your formula sheet, the table in your formula sheet has a little bit more information, but it's essentially the exact same table. We have the exact same table here, okay? And then we're also told where FE is equal to this term right here, which basically allows you to solve based on this upper table. So let's use this problem to try and solve what we're looking for, essentially, and then we'll go from there. Okay, so going back to our lecture notes, so it's exactly the same table. You can use 11.1 or you can use your table in your formula sheet. Then 11.2 we've seen in a previous video. 11.2 is available here, so we'll reference it whenever we need. I'll actually leave it here, and we'll reference it if we need to directly in the lecture notes. Let me just copy it over down to the bottom here so that we have it in our notes at the bottom as well. Okay, so let me copy it over so we have both available, and then we'll start solving the problem based on this. Okay. Okay, so it says determine the equivalent radial load. So first of all, before even getting started with determining the radial load and trying to understand what's happening, let's first write down our givens and maybe do a quick diagram of the bearing. So what I like to do is I like to draw my bearing in the same way as the form that I drew it earlier in the diagram in 2D with a cross section. And I know that my cross section has an F radial that's equal to 5 kilonewtons, and I'm also told that there's an F axial that is equal to 2 kilonewtons. And I'm also told in the problem that we're told that the inner ring rotates at 400 RPM. So I know that it's going to be an inner ring rotation problem. And because it is an inner ring rotation problem, I'm going to say that V is going to be equal to 1. So I already know that my V value is going to be equal to 1. Okay, now based on that, I can then start solving for my problem. So what I'm going to do is I'm going to go under and I'm going to write down my equation to find my F equivalent. So my equation is FE. If I rearrange the equations that I've written before, FE is going to be equal to XV FR plus Y FA. Okay, and if I look at my formula sheet, I can go find that in my formula sheet. I'm essentially using this equation right here. Okay, I'm not yet thinking about the i's yet, but I'll think about the i's, whether the I is 1 or 2. So based on the table, whether it is these terms that we're going to use or these terms that we're going to use. Okay, but that essentially gives me the equation to find FE. Okay, I'm just using the representation of the graph to find FE. So if we were to show the graph really quick again, I would just have the graph with my E value right here, and I know there's a straight line before, and there's an angled line at the top, and what I'm looking for is X and Y. But what I need to figure out is whether FA over VFR is greater than or less than E. Okay, this is what I need to figure out. I need to figure out this term first, because that's going to determine whether or not I'm going to use this part of the graph or this part of the graph. Okay, so that's the first step in trying to figure out what my FE is equal to, because I need to find, essentially what I need to do is I need to find my X and my Y. Now, if we have a FA over VFR that's less than E, then I'm just going to use that FE is pretty much equal to VFR. Now, if my term is greater than E, it complicates the problem slightly. So let's look at this problem specifically. So we can actually find out, we have FA and we have FR. We also have V. So we can say that FA over VFR, we can find a number for it, is going to be equal to 2 over 1 times 5. Okay, it's 2 kilonewtons over 5 kilonewtons. Okay, and we get that this is equal to 0.4 as a ratio, so it's 40%. So now we need to find our E value in comparison, or to be able to compare our FA over VFR value. Okay, so we know our FA over VFR value is 0.4. So now we need to find E in terms of figuring out what we need. So if we go back to our chart above, or our table 11.1, we now have FA over VFR. And what we need to figure out is, let me erase all this so that we have it, so that we can see it. So we have FA over C0, we have an E value, and we already have our FA over VFR. And what we need to figure out is FA over VFR greater or less than E? So in order to find E, what we're going to do is we're going to find FA over C0. Okay, and FA over C0, what it is the axial force over the basic static load rating. Okay, and the basic static load rating is given by the catalog. It's essentially the first rating where the bearing would fail. Okay, and based on that, we can find an E value that's equivalent. So if you get, for example, an FA over C0 of this, it would be equivalent to this E. Okay, and you might have to interpolate between lines if you don't get an exact FA over C0 from the table. So going back to our problem, we can see we're told that we have a 0.2 single row deep groove ball bearing with 30 millimeter bore. So we're given the information on the ball bearing. The information on the ball bearing is given, and we're told that we have a 30 millimeter bore, and we're told that we have a deep groove bearing. So we have a C10, which we've used previously, of 19.5, and a C0 of 10. So we can see that the C0 is always less than the C10 because that would be essentially the first failure, whereas C10 would be after 10% of failures. Okay, so the value is 10. So now what we can do is we can find FA over C0. So we can say, let's compare our FA over VFR to E, and in order to find E, we need to find, so step 2 is find your FA over C0 in order to find E. And your FA over C0 is 2 divided by 10. Okay, so we're told it's 2 kilonewtons divided by 10 kilonewtons. So we get a value of 0.2. And if we go to our chart, so either 11.1 or our formula sheet, we'll see that E is a value. So we have E is going to be a value equivalent to where 0.2 is. So E is going to be anywhere from, and be careful with the decimals here, but E is going to be between 0.34 and 0.38. Okay, we can see that FA over C0 is between those two. So then we can interpolate between those two, but we don't need to interpolate just now. We can interpolate a little bit later. First, we can figure out if E is going to be greater or less than FA over VFR. And we know that FA over VFR is equal to 0.4. We also know that E is going to be a value that we might have to interpolate to of 0.34 to 0.38. But before interpolating, just check your values. Clearly, the value of E is going to be something like 0.35 or 0.355 or something like that. And clearly, that's less than FA over VFR. Now, if it's less than FA over VFR, what is the value that we would have to use in order to solve for this? So going back to our table 11.1, we can see that FA over VFR is greater than E. Therefore, we're going to use X2 and Y2 to solve our problem. So it's actually the more complicated way. If it was X1 and Y1, it'd be very easy. We wouldn't even have to interpolate, but because it's X2, Y2, we're going to have to find a true value of FA over C0 and find a value to interpolate between these two values as well. So we would have to interpolate between these two values or just interpolate between the values of Y2 between the two values, okay, based on our FA over C0 that we have. And hopefully you know how to interpolate from now, especially if you've taken thermodynamics, which all of you should have taken. But essentially interpolation is very easy. You can look it up and you can do it yourself. I'm not going to go over how to interpolate between two values in a table, but what you would do is you would then go about, you would say we have to use X2 and Y2 because FA over VFR is greater than E, and your X2 value you don't have to interpolate because it's always a constant, it's 0.56. Your Y2 you would, however, have to interpolate, and that value would be 1.27, and I'll write through interpolation. Okay, so that you know you have to interpolate. And then your FE value is going to be equal to X2 VFR plus Y2 FA based on our theory and based on the equation being rearranged. And if you plug in all the values, you get 5.34 kilonewtons. Okay, so we've been able to solve for FE. So we're done with part A of the problem. Now, what we need to do is we need to solve for part B of the problem. Now, quick note about part A of the problem. Instead of using an F radial of 5, if it didn't have any axial force, now we're using an F radial of 5.34 essentially, or F equivalent of 5.34. So whenever we're solving the problem, we know that the equivalent load is a little bit higher than the radial load alone. So it's going to damage the problem. It's going to damage our bearing a little bit more than initially. Okay, so now let's do part B of the problem. And part B of the problem is going to use more of the traditional stuff that we've learned in previous videos. So let's go to part B of the problem and read through. It says, determine the predicted life in revolutions that this bearing could be expected to give in this application with a 99% reliability. So they want us to look for a 99% reliability, and they want us to tell us what this bearing is going to go through based on our force desired, okay? And clearly our force desired is not going to be just our radial force, it's going to be our equivalent force. So what we're looking for is what life desired we could be looking for, or what life L sub D we could be coming up with in terms of the given bearing that we have. So our force desired, we know, is equal, because of the calculations that we know and because of the loading that we know, is going to be equal to 5.34 kilonewtons. So in this case, our force desired is equivalent to our force equivalent, which we found in part A. Okay, instead of 5, it's going to be 5.34 because there is an axial loading. Now, LR, just to write it down, or life rated, is 10 to the 6, okay, revolutions. That's not going to change. And then we're also given that our system is rotating at 400 RPM, so we could find it in hours if we want to. And we know from our table 11.2, we already went to our table 11.2 and found that our C10 value, or our 90% reliability value, is equal to 19.5 kilonewtons. And then this is for a reliability of 0.9. Okay, so we have this information from table 11.2. Okay, so if we try and solve our problem, what we can say is we know that we also want a reliability of 0.99. So what we're going to have to do is we're going to have to translate our system to a certain reliability, and then we're going to have to rearrange our equation to find our x value. okay? So let's write the equation whenever we have a different reliability than 0.9. Let's write our equation for C10 for that. So what we're going to do is we're going to write we could write either, so going back to our formula sheet, we could use either this equation, which is slightly more accurate, or this equation, which is slightly less accurate. And we can go from there. We can write that equation down, and then we'll look at what we're looking for in that equation. Okay, so I'll skip a step first, and I'll write down the equation, and then I'll figure out what I'm looking for. Okay, so let me write the equation. So we have that C10 is equal to AF times FD, all multiplied by XD over all of our values for our all of our values that are at the bottom of the equation, which are Weibull parameters, and then that's all to the power of 1 over A. Okay, so let me just write the A again, 1 over A. Okay, and what we're looking for is we're looking for our life desired. So if we're looking for our life desired, we can say that we can find life desired from XD, because XD is equal to LD over LR, and we already know what LR is. So we can find LD from that, okay? So what we need to do is we need to rearrange this top equation into a term that's equal to XD. So the first thing we can do is I'm going to edit directly in the top equation. I'm going to put C10 to the power of A, AF times FD to the power of A, all to the power of A, and then that would be A to the power of A, which would be to the power of 1, essentially. So this one would cancel, okay? So I'd be left with that, and then I can rearrange my equation to solve for XD. So the next step I can take, so a few of the terms that I can write down for all these terms. So AF, let me write it in black. AF is equal to 1. We're going to assume that we have an application factor of 1. We're not given any application factor in the problem. Then for the bottom of that equation that I didn't write down, we have x0, theta, and b. So b is 1.483, theta is 4.459, and x0 is 0.02. And then we have that A is equal to 3 because it's a ball bearing. And based on that, I can rearrange the top equation to try and find XD. So the first step I'm going to do is I'm going to bring it over everything to the left that I can. So I'm going to have C10 over AF times FD to the power of A is going to be equal to XD divided by the Weibull parameter terms. Okay, and then based on that, now I'm going to actually write my Weibull parameter terms out. I'm going to bring all the Weibull parameters to the top left of the equation. So I'm going to have that C10 over AF times FD all to the power of A multiplied by x0 plus theta minus x0 times 1 minus RD. So I'm using the simplified equation, okay? So I'm using the equation that's a little bit simpler, to the power of 1 over B, and I'll keep those in square brackets so that we don't confuse it with the other one, is equal to XD. And if we solve for this, if we plug in all the numbers, we have everything in this equation, we find that XD would be equal to 10.66. And then based on that, we can say that LD would be equal to 10.66 times LR, essentially. So 10.66 times LR, which is 10 to the 6th, and so I'll just write that this is 10.66 times 10 to the 6 revolutions. Okay, so that means that at a 99% reliability, we can use this bearing based on the loading parameters that were given in the problem. We can use this bearing for 10.66 times 10 to the 6 reps. Now, if we go back to our problem, that solves hopefully our part B, but it tells us one more little thing. It says determine the life in revolutions, so we've solved it. Now, the other thing we can do is we can try and figure out how many hours. So this question could also ask you to determine the predicted life in hours. Okay, we have it in revolutions, but revolutions, the problem is that it doesn't really give us a good measure of like how long that it actually is for the bearing. So we can convert to life in hours if we want, because we're given the rotation speed. So we're given that we have 400 RPM, therefore we can convert to find our cursive LD as well. Okay, this is an extra, this is our final answer, okay, but we can go further and we could say that LD is equal to 10.66 times 10 to the 6th. That's the value of our, that's our value in terms of revolutions. And then we would divide that by 60 times 400 based on our conversion between cursive LD and our regular LD. And we get a value of 444 hours. So that means it can last for 444 hours. Okay, so hopefully this example makes sense. If you have any questions, again, feel free to reach out to me. And in the next video, we're going to do another example of this just to make sure that we know how to work this type of problem and we make sure we understand what's happening when we're already given a bearing and we're told there's a certain loading parameter. How do we actually go and figure out this bearing? Okay, so we're going to do another type of problem where we're looking for the actual bearing and we're looking for selection of a bearing as opposed to already having the bearing in the question. So we'll see you in the next one for that example problem.